Why do financial returns often look calm for weeks and then suddenly turn turbulent? The direction of each return may remain hard to predict, yet the size of the moves is clearly persistent. Large changes up or down tend to be followed by more large changes, while small changes cluster together. This is volatility clustering. It motivates the ARCH model, our first framework, for allowing conditional risk to change over time. The conditional mean and the conditional variance answer different questions. The conditional mean is our best forecast of the level of a variable, given information available yesterday. The conditional variance measures the uncertainty around that forecast. An autoregressive moving average model may describe predictable movements in the mean, while a volatility model describes predictable movements in the variance. A series can therefore be unpredictable in sign, but highly predictable in the magnitude of its next movement. Let me separate three ideas about disturbances, because they are easy to confuse. Shocks that are independent and identically distributed are independent of the past, and all share one distribution. A martingale difference sequence asks less. It only requires that the expected shock today, given the past, is zero. White noise requires a zero mean, a constant unconditional variance, and no serial correlation. Notice that none of these force a constant conditional variance. In fact, uncorrelated shocks can still have correlated squares, and that is exactly where volatility models begin. The autoregressive conditional heteroskedasticity model, or ARCH model, makes current variance depend on past squared shocks. In an ARCH-1 model, the conditional variance at time t equals a positive intercept, called alpha 0 plus alpha 1 times the squared shock at time t minus 1. Squaring removes the sign and measures the magnitude of yesterday's surprise. A large surprise raises today's predicted risk, while a small surprise allows predicted risk to return toward its normal level. We can represent the shock at time t as the conditional standard deviation at time t multiplied by a standardized innovation. The standardized innovation has conditional mean 0 and conditional variance 1. This decomposition separates scale from direction. The variance recursion determines how large the next shock is likely to be, while the standardized innovation determines its sign and exact realization. A common mistake is to treat the fitted conditional variance as the shock itself. It is a forecast of uncertainty, not an observed return. The ARCH-1 coefficients must respect basic constraints. Alpha 0 must be positive, and alpha 1 must be non-negative, so that predicted variance cannot become negative. If alpha 1 is below 1, the process has a finite, constant, unconditional variance. That unconditional variance equals alpha 0 divided by the quantity 1 minus alpha 1. Conditional variance moves over time, but unconditional variance averages those movements over the entire stationary distribution. Conditional heteroskedasticity and constant unconditional variance are therefore compatible. An ARCH model of order P adds several lagged squared shocks. The conditional variance equals an intercept plus a weighted sum of squared shocks from the previous P periods. Each alpha coefficient measures the direct effect of a shock at its particular lag. Non-negative coefficients preserve non-negative variance. A finite unconditional variance requires the sum of the lag coefficients to be below 1. The model is intuitive, but a large value of P can consume many parameters and produce an irregular response pattern. ARCH models can also be viewed as autoregressions for squared shocks. The squared shock equals its conditional variance plus a new disturbance, so an ARCH model implies serial dependence in the squares even when the original shocks are uncorrelated. This observation gives a practical diagnostic. After estimating a conditional mean model, inspect the residuals and their squares. Serial correlation in the residuals suggests a mean problem. Serial correlation in squared residuals suggests neglected conditional heteroskedasticity. One approach is to examine the autocorrelation function of squared residuals and apply a portmanteau test. Another is Engels-Lagrange multiplier test, which regresses squared residuals on a constant and several of their own lags. The null hypothesis says that all lag coefficients are zero, so there is no ARCH effect up to the chosen order. A rejection supports time-varying conditional variance. Failure to reject does not prove homoskedasticity, because power depends on sample size and lag choice. Stationarity asks for more than non-negative fitted variances. For an ARCH-1 process with a standardized innovation, the variance recursion behaves like an equation whose coefficient is itself random. A finite second moment needs alpha 1 below 1. Strict stationarity is weaker. It can still hold under a condition on an average logarithm, even when some familiar moments do not exist. This matters for financial data, because heavy tails can make the high moments unstable. So we should always state which kind of stationarity and which moments each of our results actually needs. In empirical work, first specify a plausible conditional mean, then estimate its residuals, and only then model their conditional variance. Scale the data sensibly, check whether a few extreme observations dominate the fit, and compare several lag orders using both diagnostics and information criteria. Do not choose a complicated ARCH order solely because it lowers an in-sample criterion slightly. The aim is a stable volatility recursion that captures persistence and leaves standardized residuals without systematic dependence. When you read R output, keep the variance equation separate from the mean equation. A significant lagged square supports a short-run news response, but its size depends on the scale of returns. Plot the fitted conditional standard deviation, not the variance, when you want units comparable with returns. Then divide the residuals by that fitted standard deviation and look at both the standardized residuals and their squares. Successful estimation is only the beginning. The standardized series is what tells us whether the volatility pattern still remains. ARCH forecasts also have a clear boundary. They predict the conditional second moment from observed past surprises, not the exact size of tomorrow's return. A high variance forecast means a wider distribution of plausible outcomes, including both gains and losses. It does not forecast a market decline. Confusing volatility with direction can turn a sound risk model into a misleading trading claim. Any directional forecast must come from the conditional mean or another explicitly modeled feature. The conditional distribution also matters for risk. If standardized innovations are assumed normal, the fitted variance determines a conditional normal density. Financial residuals often have heavier tails, so a normal ARCH model can understate extreme loss probabilities even when its variance recursion is useful. Comparing normal and heavy-tailed innovations separates a scale model from a distributional assumption. ARCH creates nonlinear dependence that ordinary autocorrelation can miss. The raw shocks can be serially uncorrelated, while their squares and absolute values remain predictable. This is why a white noise conclusion for returns does not end the analysis. Diagnostics should examine the transformations linked to the economic target, especially squared residuals for variance and tail indicators for extreme risk. The central lesson is that unpredictability in levels does not imply unpredictability in risk. ARCH converts the visible clustering of large and small movements into a conditional variance forecast based on past squared shocks. Its strengths are transparency and direct interpretation. Its main limitation is that long persistence may require many lags. That limitation leads naturally to GARCH, which summarizes a long history of shocks through a much more parsimonious recursion. We ended the last lesson with a problem. An ARCH model may need many lagged squares just to reproduce slowly decaying volatility. Let me show you how the generalized ARCH model, or GARCH model, fixes this by adding lagged conditional variance. In a GARCH 1-1 model, today's conditional variance equals an intercept plus alpha times yesterday's squared shock plus beta times yesterday's conditional variance. Alpha measures the immediate reaction to new information. Beta carries past volatility forward. Together they give us persistent but parsimonious risk dynamics. The general GARCH model can include P lags of squared shocks and Q lags of conditional variance. In practice, GARCH 1-1 is often a strong baseline because it uses only 3 variance parameters. The intercept sets the long-run scale. The ARCH coefficient controls how sharply volatility reacts to fresh news. The GARCH coefficient controls how slowly the effect fades. A high beta does not by itself imply a large response to news. Persistence and impact are different features. To keep the conditional variance positive in the standard specification, the intercept is positive, and the shock and variance coefficients are non-negative. For a weakly stationary GARCH 1-1 process, alpha plus beta must be below 1. The unconditional variance then equals the intercept divided by the quantity 1 minus alpha minus beta. When the sum is close to 1, volatility is highly persistent, and the long-run variance becomes very sensitive to small estimation errors. Repeated substitution reveals why GARCH is parsimonious. Today's variance can be written as a constant plus an infinite sequence of past squared shocks. The weights decline geometrically at rate beta. Thus, GARCH 1-1 behaves like an infinite-order ARCH model whose lag pattern is smooth rather than freely estimated. A recent shock receives weight alpha, the preceding shock receives alpha times beta, and older shocks receive progressively smaller weights. This structured decay saves parameters and stabilizes estimation. Weak stationarity concerns constant first and second moments and covariances that depend only on distance in time. For a general GARCH model, a finite unconditional variance requires the sum of all ARCH coefficients and all GARCH coefficients to be below 1. This condition is easy to interpret, but it is a moment condition. It should not be confused with the broader question of whether the full probability distribution is invariant over time. For GARCH 1-1, strict stationarity is governed by the average logarithmic growth of the random coefficient beta plus alpha times the squared standardized innovation. The required expected logarithm must be negative. This condition can hold even when alpha plus beta is at least 1. In that case, the process may have a stable time invariant distribution, but no finite unconditional variance. Strict stationarity does not automatically deliver weak stationarity or finite moments. This distinction also helps explain heavy tails. A GARCH process can produce a stationary distribution with far more probability in the tails than the innovation distribution alone would suggest. Even if each shock is conditionally normal, the returns need not be normal overall, because the changing scale mixes together many normal distributions with different variances. Higher moments are harder to pin down than the second moment. So, a fitted model can have a finite variance and yet an infinite theoretical fourth moment, and that matters for kurtosis and for our standard errors. So far, our models have used squared shocks, which means they ignore the sign of the news. A positive surprise and a negative surprise of the same size push next period's variance up by exactly the same amount, but equity data often tell a different story. A drop tends to raise future volatility more than an equally large rise. We call this an asymmetric volatility response, and it is often linked to leverage, changing financial risk, investor behavior, and market frictions. The economic story should be used carefully. A falling equity value can raise a firm's debt-to-equity ratio and make its equity riskier, which is the traditional leverage explanation. Market stress, constrained trading, and rapid reassessment of downside risk can also amplify negative news. The empirical fact is an unequal conditional variance response. A volatility model identifies that response from data, but it does not by itself prove which economic mechanism caused it. Exponential GARCH, or ARCH, models the logarithm of conditional variance. The log variance depends on its own lag, the signed standardized shock, and the magnitude of that standardized shock. Taking the logarithm guarantees a positive variance without imposing non-negative coefficients on every term. The signed component creates asymmetry. When its coefficient is negative under the usual convention, a negative standardized shock raises log variance more than a positive shock of the same size. The magnitude term in ARCH captures the general effect of surprising news, regardless of sign. The signed term tilts that response toward good or bad news. Because shocks are standardized by their conditional standard deviation, the model judges news relative to the risk that was expected at the time. A raw return of 2% can be enormous in a quiet market, but ordinary in a crisis. Standardization lets the model distinguish those situations. The GARCH model adds an indicator for negative lagged shocks to the ordinary variance recursion. Today's variance includes the usual intercept, lagged variance and squared shock, plus an extra squared shock effect when yesterday's shock was negative. A positive extra coefficient means bad news has the larger impact. Unlike ARCH, this model works directly with variance, so parameter restrictions must still ensure that the fitted variance remains non-negative and that relevant moments exist. A news impact curve summarizes the fitted relationship between yesterday's shock and today's variance while holding lagged variance fixed. Standard GARCH produces a symmetric curve around zero. An asymmetric model produces different branches for positive and negative shocks. The curve is a useful communication device because it reveals both curvature and direction. However, it is a conditional model summary, not a causal graph. Its shape depends on the specification and the chosen reference variance. Threshold models offer related ways to separate regimes created by shock signs. A threshold GARCH model can assign different squared shock coefficients to negative and non-negative innovations. A threshold ARCH model may describe conditional standard deviation using absolute shocks with different slopes on the two sides of zero. These models are easy to interpret, but a hard indicator creates an abrupt boundary. If the actual response changes smoothly, a threshold specification may exaggerate the discontinuity. Some volatility changes are broader than the sign of one shock. A Markov regime switching GARCH model allows the intercept, shock response, or persistence to depend on an unobserved state. The state follows a Markov chain, So tomorrow's regime depends probabilistically on today's regime. One state may represent tranquil markets and another stressed markets. The model estimates both state-dependent volatility dynamics and transition probabilities, rather than assigning regimes from an observed recession label. Regime switching can represent sudden and persistent changes that a single GARCH recursion absorbs only through coefficients near 1. It can also allow the innovation distribution to change across states. Yet, estimation is substantially harder because the state is latent and the likelihood averages over possible state histories. Label switching, a local optima, and weakly identified transitions are practical concerns. A visually appealing two-regime plot is not sufficient evidence that two economically meaningful regimes exist. In the chapter's equity case study, symmetric GARCH is a baseline, while exponential GARCH and GARCH ask whether negative returns have an additional volatility effect. When alpha plus beta equals 1, the model is called integrated GARCH, or ARCH. The variance recursion, then, has a unit root in volatility. A shock to squared returns never fully disappears from future variance forecasts. The usual finite unconditional variance formula breaks down because its denominator becomes 0. ARCH can fit extremely persistent samples, but the implication of permanent volatility shocks is strong and often economically implausible for asset returns over very long horizons. The squared process has an autoregressive moving average representation. Under ARCH, the autoregressive root is exactly 1, so accumulated volatility innovations continue to affect the level of conditional variance. This resembles an integrated mean process, but the interpretation differs because variance must remain non-negative and evolves through squared shocks. A common error is to describe ARCH simply as an ordinary unit root applied to returns. The unit root belongs to the variance dynamics, not necessarily to the return level. Riskmetrics exponential smoothing is a special ARCH case with a zero intercept. The next variance forecast is a weighted average of yesterday's squared return and yesterday's variance forecast. A decay parameter near 1 produces smooth, persistent estimates, while a smaller value reacts faster to recent events. The method is convenient and easy to update, but it imposes permanent shock effects and lacks an independently estimated long-run variance toward which forecasts can revert. Near integrated estimates may also reflect structural breaks, omitted asymmetry, changes in trading regimes, or a poorly specified conditional mean. Before accepting ARCH, inspect the sample for level shifts and compare models that allow breaks or regimes. Estimate uncertainty around alpha plus beta rather than treating a point estimate near 1 as exact evidence. Long horizon forecasts are especially sensitive to this distinction because stationary GARCH forecasts converge to a finite long-run variance, while ARCH forecasts do not. Persistence can also be summarized through a volatility half-life. After a shock, the gap between the current variance forecast and its long-run target decays approximately at the rate alpha plus beta. The half-life is the horizon at which half that gap remains. This translation turns an abstract coefficient sum into time units. When the sum is extremely close to 1, the calculated half-life becomes unstable, so report uncertainty and avoid excessive precision. In R output, check the intercept, the news coefficient, the variance persistence coefficient, and their sum. A large beta with a tiny alpha describes slow but weak reaction to each new shock. A larger alpha describes a more responsive variance path. Plot observed squared returns beside fitted variance, but remember that squared returns are noisy proxies rather than observed conditional variance. Standardized residual checks are more informative than judging whether every fitted spike matches one realized square. Forecasts provide a useful model comparison. Stationary GARCH forecasts gradually move toward the estimated long-run variance, while an integrated specification keeps the current variance level influential indefinitely. Compare these paths over horizons relevant to the application, such as 1 day, 1 month, or 1 quarter. A model that fits daily movements slightly better may give implausible long-horizon risk. Forecast horizon should therefore influence the choice between near-integrated and mean-reverting specifications. Moment existence should be checked at the order needed for the application. The condition alpha plus beta below 1 gives a finite second moment in GARCH 1.1, but a finite fourth moment requires a stronger restriction involving the fourth moment of the standardized innovation. Tests based on squared returns and kurtosis can be unreliable in finite samples when that higher moment does not exist. GARCH 1.1 is effective because it separates news impact from persistence and compresses a long shock history into one recursion. Yet a valid interpretation depends on positivity, the relevant stationarity concept, and the moments needed for the application. High persistence is not automatically a unit root, and strict stationarity is not the same as finite variance. These distinctions prepare us to study another limitation of standard GARCH: equal treatment of positive and negative shocks. Now we need to estimate these models, and I want to show you why that takes some care. We are recovering parameters from a series whose variance changes recursively. Under a conditional normal specification, each observation contributes to the likelihood through its conditional mean and its conditional variance. A large residual is less surprising when the fitted variance is high than when it is low. The full log likelihood adds these contributions over time, while the variance at each date is built from earlier residuals and earlier fitted variances. For a GARCH 1.1 model, the unknown variance parameters are the intercept, the response to the previous squared shock, and the persistence of the previous variance. Mean parameters may be estimated jointly or specified separately. The likelihood balances two terms. One penalizes a large conditional variance, and the other penalizes a squared residual relative to that variance. Setting variance too high everywhere and setting it too low around large shocks both reduce the likelihood. The recursion needs an initial conditional variance before the first observation can be evaluated. Common choices include the sample variance, the model's implied unconditional variance, or a backcast that weights early squared observations. With a long stationary sample, reasonable initializations often have little influence on final estimates. In short or highly persistent samples, initialization can matter. It should be reported, and robustness to alternative starting values should be checked rather than silently assumed. Numerical optimization is necessary because the likelihood is non-linear and the variance depends recursively on parameters. Starting values must satisfy positivity and stationarity restrictions appropriate to the model. It is good practice to use more than one set of starting values, inspect convergence codes, and compare the final objective values. A software message saying that optimization finished does not guarantee a global maximum, economically sensible parameters, or a correctly implemented likelihood. The score is the derivative of the log likelihood with respect to the parameters. Because each variance depends on earlier variances, score calculations also propagate through time. Reliable software evaluates these derivatives analytically, automatically, or numerically. Near-boundary estimates can produce unstable derivatives and a flat likelihood surface. Standard errors based on a poorly conditioned Hessian may then be misleading, so convergence and curvature diagnostics are as important as the reported coefficient table. Conditional normality is often a convenient working assumption rather than a literal belief. Financial standardized residuals can remain skewed or heavy-tailed. Gaussian quasi-maximum likelihood uses the normal likelihood to estimate the conditional mean and variance parameters, even when the true innovation distribution is not normal. Under suitable stationarity, moment, and regularity conditions, the parameter estimator can remain consistent for the correctly specified variance recursion, but its conventional normal standard errors need adjustment. Quasi-likelihood consistency does not excuse a wrong conditional variance model. It protects against misspecification of the innovation density under stated conditions, not against omitted lags, missing asymmetry, structural breaks, or an incorrect mean. The required moments also matter. If tails are so heavy that the necessary moments fail to exist, familiar asymptotic results may not apply. A robust label should never replace a careful examination of the model and the data. Two matrices show up when we compute standard errors. One comes from the expected curvature of the objective, the other from how much the score varies. If the likelihood is correctly specified, a result called the information matrix equality says these two coincide, and we can use either. Under quasi-likelihood, they generally differ, so we combine them in what is called a sandwich estimator, wrapping the score variability inside the inverse curvature. Let me stress the practical point. When normality is only a working assumption, this robust sandwich covariance should be our default. Distributional alternatives can improve density and tail forecasts. Student-type innovations allow heavier tails, and skewed distributions can represent asymmetry in standardized shocks. These choices change the likelihood, and sometimes the fitted volatility parameters. They should be compared using diagnostics and forecast goals, not chosen only to improve an in-sample likelihood. A better innovation density cannot compensate for a variance recursion that misses persistence, leverage, or regime change. Forecasting follows directly from the fitted recursion. A one-step variance forecast uses the latest squared residual and fitted variance. Longer horizon stationary GARCH forecasts gradually approach the estimated unconditional variance. For ARCH, the effect of current volatility does not mean revert in the same way. Parameter uncertainty is often ignored in routine forecasts, but it can be substantial when persistence is near 1. Risk intervals should acknowledge both future shocks and estimation uncertainty where feasible. A disciplined estimation workflow fits the conditional mean, estimates a parsimonious variance model, checks optimization, computes quasi-likelihood robust standard errors, and examines standardized residuals. It then compares alternative distributions or asymmetric terms and evaluates forecasts on data not used for fitting. Scaling returns, for example in percentage units, may improve numerical stability, but it changes the intercept scale. Every reported parameter must be interpreted on the scale actually estimated. Joint estimation of mean and variance parameters can be efficient, but it also links their numerical behavior. A misspecified mean leaves predictable structure in residuals and can distort variance estimates. Conversely, severe volatility changes affect the precision of mean coefficients. Compare the joint fit with a carefully specified mean benchmark and inspect residual autocorrelation. Robust variance modeling does not eliminate the need for a credible conditional mean, even when the empirical focus is risk. Software often enforces positivity through parameter transformations rather than rejecting every invalid trial value. This helps optimization but can place estimates very near a boundary where standard quadratic approximations are poor. Check whether reported constraints apply to positivity, weak stationarity, or both. A parameter printed just inside the admissible region may have an asymmetric sampling distribution. In that setting, profile likelihood, simulation, or bootstrap intervals can be more informative than a symmetric standard error. When comparing normal and heavy-tailed likelihoods in ARCH, do not compare raw parameter names without checking how each distribution is standardized. A scale parameter in the innovation density should preserve conditional variance 1 for the standardized shock. Use probability integral transform, diagnostics, or quantile plots to assess the full conditional distribution. If the goal is value at risk, evaluate tail exceedance frequency and clustering, because a good volatility path does not guarantee accurate conditional tail probabilities. The outer product of scores and the negative Hessian provide two different covariance ingredients. Under a correctly specified conditional density, they agree in expectation, but under quasi-likelihood, they need not. Computing the full sandwich makes that distinction operational. Reporting only the inverse, Hessian silently restores the normal likelihood assumption that quasi-maximum likelihood was meant to relax. Boundary cases need special inference. Testing whether an ARCH coefficient is exactly 0 places a non-negative parameter on the edge of its admissible set, while testing integrated persistence places a sum on a stationarity boundary. Standard symmetric normal or chi-squared approximations may then fail. Simulation bootstrap or specialized reference distributions are preferable when the tested restriction is genuinely on a boundary. The main lesson is that GARCH estimation is not a push-button exercise. The likelihood connects residual size to time-varying risk, but initialization, constraints, optimization, distributional assumptions, and covariance estimation all affect inference. Gaussian quasi-maximum likelihood is powerful because it separates variance modeling from exact normality. Its validity still depends on a correct conditional variance structure and adequate moments, followed by diagnostics that test what the fitted model leaves unexplained. Model comparison should combine likelihood-based criteria, parameter plausibility, standardized residual diagnostics, and forecast performance. An asymmetric coefficient that is statistically noticeable but economically tiny may not improve risk forecasts. Conversely, a modest average improvement may matter greatly during large negative market movements. After you fit an asymmetric model, examine its standardized residuals and their squares, exactly as we did with symmetric GARCH. Plot the news impact curve and always verify the sign convention your software uses. Check that the persistence is still compatible with the moments you need. For regime models, inspect the smoothed state probabilities and the transition estimates. And please do not pick a model just because it has more parameters and a higher likelihood. Use an information criterion and out-of-sample evaluation instead. Let me talk about diagnostics, because they do two jobs for us. Sign conventions deserve special attention in R. Some functions define the innovation as observed return minus fitted mean, while others display model terms whose signs differ from an intuitive leverage coefficient. Before declaring that bad news raises volatility, calculate fitted variance for one positive and one negative shock of equal magnitude, while holding the past variance fixed. This direct numerical check is clearer than relying on a coefficient label, especially for exponential specifications. Innovation, distribution, and asymmetry can interact. A symmetric heavy-tailed distribution may explain frequent extreme shocks, without explaining why negative shocks affect future scale differently. A skewed distribution can describe unequal contemporaneous tails, while an asymmetric variance recursion describes unequal dynamic responses. These are distinct features. Compare them separately and examine whether the leverage effect survives after allowing heavy tails or skewness, rather than assigning every downside pattern to one asymmetric coefficient. Before we estimate anything, they ask whether conditional heteroskedasticity is even present. For regime switching, transition probabilities imply expected regime duration. A state with a high probability of remaining active should produce sustained episodes, whereas a low persistent state may capture isolated extremes. Translate estimated transitions into expected durations and compare them with the plotted state probabilities. If a regime appears for only a few observations or changes whenever one outlier arrives, it may be compensating for an inadequate innovation distribution rather than revealing a stable economic state. Forecast comparison should respect the different objects these models produce. An asymmetric GARCH model conditions on the observed sign and size of recent news. A regime model also averages over uncertainty about the current latent state and its future transitions. Comparing only fitted variances ignores state probability uncertainty, so use the full predictive variance or density generated by each model. Parameter stability is another useful discriminator. If a symmetric GARCH fit shows instability, while an asymmetric specification is more stable, omitted leverage may be masquerading as changing parameters. The reverse can also occur when one crisis dominates the asymmetry estimate. Stability tests, rolling estimates, and sub-period forecasts help distinguish a persistent response pattern from one historically unusual episode. After we estimate, they ask whether our chosen model has actually removed it. Asymmetric and regime-switching models answer different questions. A plot of returns can reveal clusters of large and small moves, but that visual evidence is only a starting point. Asymmetric models let the sign of news change the volatility response within one continuous system. Regime models let the whole volatility mechanism change across latent states. Both can reduce the false appearance of integrated persistence in a misspecified symmetric model. Their flexibility is valuable, but it raises the burden of interpretation, numerical checking, and forecasting validation. The simplest adequate model remains the preferred starting point. Our formal tests use residuals from a conditional mean model and focus on their squares because volatility is about magnitude, not direction. Begin with the conditional mean residuals. Their autocorrelation should be small if the mean model is adequate. Then examine squared residuals or absolute residuals. Significant serial dependence in these transformations indicates predictable scale. This distinction prevents a common error, adding a volatility model to compensate for a neglected mean pattern. Mean and variance specifications should be diagnosed separately, even though they are often estimated jointly in the final model. Ingalls-Lagrange multiplier test regresses squared residuals on a constant and a selected number of lagged squared residuals. Under the null hypothesis, the lag coefficients are jointly zero. The sample size, multiplied by the regression's R squared, has an asymptotic chi-squared distribution with degrees of freedom equal to the number of lags. A small p-value indicates remaining RH effects. Lag order should reflect data frequency and plausible persistence, not be chosen after searching for significance. The MacLeod-Lee test adapts a portmanteau idea to squared residuals. It combines several autocorrelations of the squared series into one statistic. The null says that these autocorrelations are jointly zero through the selected horizon. This test can detect distributed remaining dependence that no single lag reveals. Like every portmanteau test, its conclusion depends on the lag horizon, sample size, and estimation effects. Report those choices rather than presenting only a p-value. After fitting GARCH, use standardized residuals, defined as residuals divided by their fitted conditional standard deviations. If the variance model is adequate, standardized residuals should have stable scale and little serial dependence. Test both the standardized residuals and their squares. The first checks remaining mean dynamics. The second checks remaining volatility dynamics. A model can pass one test and fail the other, so a single diagnostic statistic never establishes overall adequacy. Distributional diagnostics are also important. A quantile plot or tail comparison can show whether conditional normality understates extreme standardized shocks. Heavy tails may motivate a student-type innovation distribution, but first verify that a few data errors are not responsible. Examine fitted variance paths around extreme dates and inspect whether the model reacts too slowly or remains elevated too long. These patterns can suggest missing asymmetry, breaks, or an inappropriate persistent structure. Data frequency changes what volatility clustering looks like. In the chapter's macroeconomic comparison, annual gross domestic product growth offers few observations and aggregates, much short-run variation. Monthly industrial production provides a longer, higher frequency series in which changing variability is easier to detect. A non-rejection for annual data does not prove constant economic uncertainty. It may reflect low power and temporal aggregation rather than a fundamental absence of conditional heteroskedasticity. In the reported annual growth example, the first-order ARCH statistic is about 0.06, and the 4-lag MacLeod-Lee statistic is about 5.24, both below the relevant 5% reference value. For monthly industrial production, the 12-lag MacLeod-Lee statistic is about 579, giving overwhelming evidence of volatility dependence. Conversely, high-frequency data can contain calendar effects, market microstructure noise, and outliers that imitate volatility dynamics. Before fitting GARCH, align dates, handle missing observations consistently, and understand whether returns overlap. Scaling and seasonal adjustment should be documented. Diagnostic tests assume that the analyzed residual sequence corresponds to one coherent model. Mechanical application to a poorly constructed series can produce precise answers to the wrong question. For equity returns, symmetric GARCH provides a benchmark, while exponential GARCH and GARCH assess sign asymmetry. Compare fitted conditional volatility and standardized residual diagnostics across specifications. A lower information criterion is useful, but the asymmetry coefficient should also have the expected interpretation and improve forecasts or tail measures. If multiple models fit similarly, the simpler model may be preferable unless the application specifically values downside responses. Markov switching can capture abrupt changes that remain in standardized residuals from a single regime model. Smoothed regime probabilities should align with sustained changes in volatility rather than isolated numerical artifacts. Transition probabilities near 0 or 1 can be difficult to estimate, and regime labels are arbitrary until interpreted. Use multiple starting values and do not call a latent state a recession without external evidence. Statistical regimes and economic classifications are not automatically identical. Forecast evaluation completes the diagnostic process. Reserve a holdout period and compare variance forecasts using loss functions suited to latent volatility, often with squared or absolute returns as noisy proxies. For risk management, also examine exceedances of value at risk forecasts. in sample residual tests and out-of-sample performance answer different questions. A model that fits historical volatility closely may forecast poorly because it has overreacted to idiosyncratic events. Diagnostic p-values should be read as a profile across horizons, not a sequence of independent prizes. Testing many lag orders and reporting only the smallest p-value creates selection bias. Choose a few horizons with economic meaning, such as a trading week or month, and show them together. When the fitted model consumes parameters, use test versions or simulation procedures that account for estimation where available. Borderline results deserve sensitivity analysis, not a categorical pass or fail label. Graphical checks often reveal failures that one omnibus statistic hides. Plot standardized residuals through time, their squares, their autocorrelations, and the fitted volatility path. Compare empirical and model-based tails with a quantile plot. Mark major outliers rather than deleting them automatically. If one date drives the result, investigate the observation and the economic event. Then report fits with and without it when justified. Robustness analysis is more informative than an undocumented removal. Risk forecast evaluation should match the decision. A variance loss assesses the conditional second moment, while value at risk exceedances assess a specified quantile. Expected shortfall asks about the average loss beyond that quantile. A model can perform well for one target and poorly for another. Backtests also require enough exceedances to have power. Selecting a model for capital or portfolio decisions should therefore use the loss and horizon that correspond to that use. The macro comparison also illustrates why one test order should not be described as every possible ARCH test. The auxiliary regression in the chapter uses one lagged square, while the MacLeod-Lee calculation uses a broader truncation horizon. Degrees of freedom and lag definitions must match the statistic actually computed. A generic software label can easily conceal that important distinction. Let me leave you with the workflow. First, plot the returns and fit the conditional mean. Then, test the squared residuals for clustering, estimate a parsimonious volatility model, and standardize the residuals. Now, repeat the tests, inspect the tails, and evaluate forecasts out of sample. The mistakes I want you to avoid are testing raw returns instead of mean residuals, forgetting to standardize after GARCH, choosing lags opportunistically, and reading a non-rejection as proof. Diagnostics are not ceremonial. They tell us whether our conditional variance estimates are credible enough for real economic and risk decisions. Risk rarely involves one asset in isolation. A portfolio depends on each asset's variance and on how assets move together. Even if individual volatilities are modeled well, assuming constant covariance can misstate diversification precisely during market stress. Multivariate volatility models describe a conditional covariance matrix that changes over time. The diagonal entries are conditional variances, while off-diagonal entries are conditional covariances. Every fitted matrix must be symmetric and positive semi-definite. Positive semi-definiteness is not a cosmetic requirement. It ensures that the conditional variance of every possible portfolio is non-negative. Estimating each covariance equation separately can violate this condition, especially in higher dimensions. Multivariate models therefore need parameterizations that preserve a valid covariance matrix. They must also control the number of parameters, which grows rapidly with the number of assets. This tension between flexibility and feasibility drives the design of the main models. An exponentially weighted covariance matrix provides a simple starting point. Today's conditional covariance matrix is a weighted average of yesterday's outer product of return innovations and yesterday's covariance forecast. The weight on the past matrix is a decay parameter between 0 and 1. A large decay parameter produces slow adjustment, while a smaller value gives more weight to recent co-movements. The same recursion updates variances and covariances in a coherent matrix form. Because an outer product is positive semi-definite and a positive weighted average of valid matrices remains valid, the exponential update preserves positive semi-definiteness. It is easy to implement and scales to many assets. However, one common decay parameter forces all variances and covariances to adjust at the same rate. It also resembles an integrated volatility model without a separately estimated long-run covariance target, so shocks can remain influential for a long time. In the chapter's exchange, traded fund illustration returns on broad United States equities, technology equities, and international equities provide a small multivariate system. The exponential estimator produces a sequence of covariance matrices from which conditional correlations can be calculated. The useful output is not a long table of numbers, but the evolving pattern. Market volatility changes. Cross-market covariance rises and falls, and correlations may strengthen in stressful periods when diversification is most valuable. At the final date, in the reported exponential weighting example, correlation between the two United States equity funds is about 0.97. Their correlations with the international fund are about 0.71 and 0.79. These are sample-specific estimates, but they show why covariance dynamics matter when assets that look distinct can move closely together. The diagonal VEC model, often called DVEC, writes each unique covariance element as a function of its own lag and the corresponding lagged shock product. It is more flexible than a single decay parameter and gives direct element-by-element dynamics. Yet the number of coefficients becomes large, and simple sign restrictions do not automatically guarantee a positive semi-definite covariance matrix at every date. This limits unrestricted VEC models in practical portfolio dimensions. The BEKK model solves the validity problem through a quadratic matrix recursion. The conditional covariance matrix equals a constant matrix product, plus a transformed lagged shock outer product, plus a transformed lagged covariance matrix. Each term is positive semi-definite under the construction, so the sum is valid. Matrix coefficients allow volatility shocks in one asset to affect the future variance or covariance of another, creating channels for volatility spillovers. In a BEKK 1-1 model, the shock loading matrix governs responses to recent innovations, while the persistence matrix carries past covariance forward. Diagonal entries describe own market dynamics, and off-diagonal entries can represent cross-market transmission. Interpretation is less direct than in separate scalar equations, because coefficients act through matrix products. One should study implied responses and fitted covariances, not read one-off diagonal coefficient as a standalone causal spillover. The chapter's bivariate exchange traded fund case estimates a symmetric BEKK model for stock and bond-related returns. The fitted output reports a stationary covariance process, strong diagonal persistence, and comparatively small cross-effects. This pattern suggests that each market's own volatility history dominates short-run dynamics, while some covariance transmission remains. Numerical estimates are sample-specific, so the broader lesson is how matrices separate own effects, cross-effects, and persistence. Model dimension is the central limitation. With more assets, full BEKK estimation becomes computationally costly and can be weakly identified. Diagonal or scalar restrictions reduce parameters but also restrict spillovers. Convergence should be checked from several starts, and covariance forecasts should be inspected for numerical stability. A valid matrix by construction does not guarantee an economically useful model, just as a flexible model does not guarantee precise estimates. Choose among exponential weighting, diagonal VEC and BEKK, according to the question. Exponential weighting is transparent and scalable for routine updating. Diagonal VEC offers element-specific dynamics but needs care with matrix validity. BEKK guarantees valid covariance matrices and permits structured spillovers, but can be difficult to estimate. Forecast comparisons should use portfolio variance or covariance loss, not only the likelihood of individual return equations. Conditional correlation is obtained by dividing each covariance by the product of the corresponding conditional standard deviations. This normalization is essential when comparing dependence across calm and turbulent periods. A rising covariance can reflect higher individual volatility even if correlation is unchanged. In R, verify that calculated correlations stay between -1 and 1, and that covariance matrices are symmetric to numerical tolerance. Small coding or alignment errors often first appear as impossible correlations. Return alignment is especially important in multivariate work. Assets traded in different markets can have holidays, time zones, and non-synchronous closing times. Merging prices without a clear rule may create artificial zero returns or lead-lag relationships that look like spillovers. Use a common calendar, document missing value treatment, and ensure that every return refers to the intended interval. A sophisticated covariance recursion cannot correct dependence created by misaligned observations. Interpret cross effects through implied responses rather than isolated coefficients. Apply a standardized shock to one asset, propagate the fitted recursion, and trace how every variance and covariance forecast changes over subsequent dates. This impulse-style display respects the matrix structure and reveals persistence. Repeat the exercise for positive and negative shocks, only if the model permits asymmetry. In a symmetric BEKK model, changing the sign of the entire shock vector may leave the outer product unchanged. Forecast losses should be evaluated on the matrix or portfolio quantity that matters. A likelihood comparison rewards a complete conditional distribution, while a portfolio variance loss emphasizes one weighted quadratic form. An estimator can fit individual variances well and still miss covariance during stress. Holding out a genuine future period prevents the recursion from being rewarded for information unavailable at the forecast origin. Multivariate volatility analysis extends the univariate insight that risk is predictable but adds dependence as a second moving target. A useful model must keep every covariance matrix valid, remain estimable at the desired dimension, and capture the co-movements relevant to the application. Matrix recursions provide one route. A second route separates individual standard deviations from correlations, leading to constant and dynamic conditional correlation models in the next lesson. A conditional covariance matrix can be factored into three pieces: a diagonal matrix of conditional standard deviations, a conditional correlation matrix, and the same diagonal matrix again. This separation is attractive because each individual variance can be modeled with a familiar univariate GARCH equation, while a second model describes dependence across standardized shocks. It also makes interpretation easier. We can ask whether portfolio risk changed, because individual markets became more volatile, because correlations changed, or both. The simplest version assumes a constant conditional correlation matrix. First, fit a univariate volatility model to each return. Then divide each residual by its fitted conditional standard deviation and estimate one correlation matrix from the standardized residuals. At every date, combine that fixed correlation matrix with the changing standard deviations. This constant correlation GARCH model is parsimonious, but it cannot represent crises in which correlations rise or structural changes in international market integration. Dynamic conditional correlation, or DCC, allows the correlation matrix to evolve. The first step is unchanged. Fit univariate volatility models and form standardized residuals. The second step updates an auxiliary covariance matrix using a long-run target, yesterday's outer product of standardized residuals, and yesterday's auxiliary matrix. One parameter controls the reaction to new standardized co-movement, while another controls persistence. Their sum below 1 gives mean reversion toward the target. The auxiliary matrix is not yet a correlation matrix because its diagonal elements need not equal 1. Normalize it by its own conditional standard deviations, dividing each entry by the square root of the relevant diagonal products. The resulting matrix has 1s on the diagonal and remains positive definite under appropriate conditions. Skipping this normalization is a serious implementation error. The DCC recursion models covariance among standardized shocks, and normalization converts it to correlation. DCC is powerful because a large system adds only a small number of common correlation dynamics parameters after fitting the marginal variance models. It can capture changing diversification, contagion, and common shocks without estimating a full unrestricted matrix recursion. The parsimony is also a restriction. Every pair shares the same broad adjustment rates, and a two-step estimator can understate uncertainty if the first-stage estimation error is ignored. In practice, estimate the univariate models carefully before interpreting dynamic correlations. Remaining volatility in standardized residuals contaminates the correlation stage. Inspect whether the auxiliary matrix stays well conditioned, and compare dynamic correlations with a constant correlation benchmark. Apparent short-lived jumps may reflect one extreme observation rather than a stable dependence change. Economic interpretation should focus on persistent patterns and events that are supported by data from several assets. The chapter's 3-fund case compares broad United States equities, technology equities, and international equities. On the final sample date, dynamic conditional correlation produces marginal variances similar to the constant correlation construction because both use the same univariate models. The main difference lies in cross-asset dependence. The estimated dynamic correlation between the two United States equity funds is slightly higher than its constant benchmark, illustrating how DCC updates current co-movement. In the reported final date matrices, the constant estimate for the two United States equity funds is about 0.91, while the dynamic estimate is about 0.93. The dynamic correlation between the technology and international funds is about 0.72. These values describe that sample and date, not permanent population constants. Another useful factorization is the Cholesky decomposition. A positive definite covariance matrix can be represented by a triangular loading matrix and a diagonal matrix of orthogonal shock variances. Transforming the original innovations by the inverse triangular matrix produces conditionally uncorrelated components. This is helpful for constructing shocks, simulations, and structural interpretations because it separates common contemporaneous movement into an ordered sequence of innovations. Cholesky orthogonalization automatically preserves a valid covariance matrix when the diagonal shock variances are positive. It is computationally convenient in larger systems and can be combined with univariate volatility models for the orthogonal components. Its main limitation is ordering. Changing the order of assets changes the triangular decomposition and therefore changes the interpreted shocks. An ordering should follow economic timing or an explicitly stated identification argument, not software defaults. For portfolio management, the final object is the forecast covariance matrix. Combine forecast standard deviations and forecast correlations. Then calculate the variance of any portfolio using its asset weights. Stress analysis can compare constant correlation, DCC, and alternative orderings or models. Forecast evaluation should examine portfolio losses and covariance accuracy. A model that estimates each variance may still fail if it understates the rise in correlation during market stress. These models also support risk attribution. The diagonal volatility matrix shows which assets contribute through their own risk. The correlation matrix shows how diversification modifies that risk. Cholesky components provide one ordered decomposition into orthogonal shocks. None is a causal model by itself. Dynamic correlation documents changing conditional association, while causal claims require additional economic restrictions and identification. This distinction is essential when discussing contagion or volatility transmission. The two DCC parameters should be interpreted jointly. The news parameter measures the response to the latest outer product of standardized residuals, while the persistence parameter carries yesterday's auxiliary dependence forward. Their sum controls mean reversion toward the long-run target. A sum near 1 creates slowly changing correlations and makes the target influential only over long horizons. Check uncertainty around the sum and inspect whether dynamic estimates move enough to justify the extra model. Correlation forecasts can become numerically unstable when assets are almost redundant or the dimension is large relative to sample size. Inspect the smallest eigenvalue of each fitted correlation matrix and the condition number used in likelihood calculations. Positive definiteness by theory can be lost through rounding or poor optimization. Regularization may be needed in large systems, but it changes the estimator and should be disclosed. Dropping a problematic asset merely to achieve convergence can distort the portfolio question. To understand Cholesky ordering, imagine equity returns placed before bond returns. The first orthogonal shock can affect both contemporaneously through the triangular loading structure, while the second is interpreted after removing the component associated with the first. Reversing the order reverses that priority and changes the shocks. Comparing plausible orderings is a useful sensitivity check. If substantive conclusions change greatly, the recursive identification is weak and should not be presented as an established causal structure. Correlation itself can be unstable near extreme volatility because a small covariance estimation error is divided by two estimated standard deviations. Confidence intervals should reflect uncertainty from both the marginal volatility fits and the correlation recursion. Two-step point estimates are convenient, but treating the first stage as known can make reported DCC precision substantially too optimistic empirically. Let me pull the whole chapter together. ARCH and GARCH model a changing variance. Asymmetric and regime models enrich how volatility responds to news. Quasi-likelihood supports estimation, and diagnostics check what is left behind. Then multivariate recursions, correlation factorizations, and Cholesky methods carry all of this over to portfolios. I want to leave you with one honest caveat. No single specification wins everywhere. The best choice balances a valid probability structure, interpretability, parsimony, diagnostic adequacy, and genuine out-of-sample forecasting performance.